Thanks. Well, thanks for the invitation. So I think the last time that I was here giving a talk in this room, it was on a very different subject. So I did my PhD here at Princeton and with Igor, and I used to work on on formal subjects, on quantum field theory and string theory. But since leaving Princeton, I've been almost exclusively focusing on dark matter. And that's not actually what I'm going to talk about today. I'm not going to be talking about dark matter. But I'm going to be talking about something very closely related, which is searches for axion-like particles, which you might expect to be in the spectrum of nature, although perhaps not making up the full abundance of dark matter. So I'm going to tell you about some work which I've done recently in this sequence of papers, and I'll also tell you about some work in progress. I want to highlight some of the people here. So Malte Buschmann is one of my postdocs at Michigan, who's actually moving here to Princeton. And he did a lot of the work that you're going to see here today. So if you have more questions than I can answer today, just keep in mind that he'll be around here in the fall. So you can ask him then. Raymond Coe is also a Michigan postdoc. And then Chris Desert and Josh Foster are two of my grad students in Michigan who did a lot of the heavy lifting, which is not going to make it into this kind of high-level overview of our work, but were really crucial in doing kind of a lot of the nitty-gritty work. And then Andrew Long was a postdoc at Michigan and is now a professor at Rice. So here's the basic idea behind what I'm going to be telling you about. This is essentially the whole theory. I'll go into more detail in this, but I'm really going to be focusing on data analysis in this talk. The idea, though, is to look for axion-like particles, which might be in the spectrum of nature, and to try to see them with data. And so what I'm going to be looking at are processes whereby we can create an axion within the core of a neutron star. From Bremsstrahlung, when you have neutron-neutron scattering through pion exchange, you can Brem off an axion. And then that axion is weakly interacting. And I'm going to use axion here to refer also to axion-like particles. These axions can escape the neutron star because they're weakly interacting and then convert into a photon in the external magnetic fields that surround the neutron stars. And then I'm going to be looking with X-ray telescopes for X-ray signatures of this process coming from neutron stars. And I'll tell you the results of searches for this process. So one crucial thing here is that these photons, the axions which emerge, their energy is going to be on the order of the core temperature of the neutron star, which for a typical neutron star is about 10 keV. If you look at a neutron star, you do see X-ray emission, and you do see electromagnetic radiation, but it's at the temperature of the surface, and the surface temperature of a neutron star, at least the neutron stars that I'll be talking about today, are much lower. They're on the order of 100 eV. So in some sense, what I'm doing is a light shining through walls experiment, but the wall is the crust of the neutron star. So there's an energy separation between the background that we know exists for neutron stars and the signal I'm going to be looking for. Whoops. So then if you plot what you expect to see from a neutron star, what we observe, this is flux as a function of energy, is the thermal surface emission, which is thermal at a temperature typically on the order of 100 eV. What I'm looking for is something which is roughly thermal at the core temperature, which is closer to 10 keV. I'm going to be working with instruments which go up to about 10 keV. So in the energy range that I'm looking for, the signature that I'm hoping to see is a very steeply rising spectrum as a function of energy. And if I see this, if I don't see this, I might be able to put a constraint on axion-like particles. If I do see it, I can still put a constraint on axion-like particles, but I can also ask the question if this might be arising from axion-like particles. So the interesting part of this story, we kind of worked out this theory, and then we actually applied it to data. And part of my motivation here for thinking about this problem in general is that there's a huge amount of archival X-ray data just sitting on servers. And there are extreme astrophysical environments like neutron stars, and it's only natural to try to put these together to see if there's already some evidence of new physics lying around in archival data sets. So we looked at this archival data, and here is one example of one of the spectra that we saw. And I'm going to explain this in a lot more detail. I just kind of want to give the brief overview right now. So this is the same thing that I just sketched on the last slide. This is the spectrum, dFdE. On the y-axis is a function of energy going up from 2 to 8 keV. What you see here is the thermal surface emission, which is well known. This is well characterized from previous studies. what hadn't been done was simply to plot that same data above 1 keV. So previously, no one thought there was any reason to look for X-ray emission above 1 keV. So we literally downloaded the data and just plotted it up to 8 keV, up to 10 keV. And what we saw was this hard X-ray signal here. There's 3 different instruments. I'll explain this in a lot more detail. There's MOS and PN, which are 2 cameras on board the XMM Newton telescope. And then Chandra is another independent satellite. And we see in all 3 of these, as I'll explain in detail, this hard X-ray signal. And so this is really what I want to focus on today. What are the implications of this hard X-ray signal? How do we go about calculating the predicted normalization from the Axion signal? And then what can we say about this in the context of both constraining the Axion model and then asking, is this possibly consistent with arising from an Axion-like particle? And if so, what are its properties and how can we constrain it with future data sets?
This is data for a particular neutron star?
Yeah, this is for a neutron star. I'm going to be talking about 7 neutron stars today, but this is one RxJ1856. And I'll tell you more about its properties as we go on.
So M7 isn't
Good. Yeah, the M7 are, yes, M stands for magnificent. So I'll tell you about these neutron stars in more detail, but there are 7 neutron stars which kind of naturally emerge as the obvious targets to look at. They're called the magnificent 7 neutron stars. Why are they magnificent? 1, they're the closest neutron stars known to Earth. And 2, they've only been seen in surface emission. So a lot of neutron stars, we see them because they're pulsars. And so we see that they have these jets and that they're emitting non-thermal emission in the jets. In order to see the surface emission from a neutron star, the neutron star has to be really close to us. So it's no coincidence that these magnificent 7 are the only neutron stars we've seen only through their surface emission, but also they're the 7 closest neutron stars that we know of.
They're not pulsars.
These are not pulsars, and that's actually going to be pretty important, and I'll touch on that later.
Where are they?
They're relatively isotropically distributed. I mean, they're in the galactic plane, but they're so close to us. They're on the order of 100, 200 parsecs away from us that there's some minor, if you plot all 7 of them, they do prefer to be in the disk, but they're so close to us that the disk is almost isotropic.
Are you going to explain the shape? I would have very naively expected it to be more sharply peaked.
So the shape, I will explain the shape in a little bit more detail for the signal. So it is roughly a thermal distribution that comes out from the Axion spectrum. It looks like so a thermal spectrum would look like has a peak, but the peak is, if you plot it in these units, it's typically on the order of 3 times the temperature, and that temperature for a 10 keV core is 30 keV.
So you haven't gotten there yet.
We haven't gotten there yet, but I'll return to that towards the end. So when you're looking at a thermal distribution at low energies, it just looks like a rising power law. And we're essentially within that limit with XMM Newton and Chandra. It's just an instrumental feature.
But it looks more like a constant than a rising power law.
Well, I'll show you this in detail. Yeah, good. Yeah. We'll look at this. Yeah. Okay. So here is, I've kind of given away the punchline, and now I want to work back to this in detail. So I'm going to give a brief overview of what I'm actually looking for. I haven't actually defined the model that I'm trying to look for. I'm going to keep this brief because I think people are probably have seen Axion overviews before. I'm then going to go and kind of outline the different steps that you need to go through to perform the theory calculation. Then once I've outlined that, I'll spend most of the time telling you about the data itself, interpretation of the data, and then what can we do in the future to learn about this more. So first, what are axions? So I'm going to start with the QCD axion. I'm not actually going to be looking for the QCD axion, but I want to motivate axion-like particles, and it's useful to start with the QCD axion. So the QCD axion was originally introduced to solve the strong CP problem, which is related to this term, which could have appeared in the QC Lagrangian, but appears for some reason to have not. Theta bar is this, you can think of it as an angle, which naturally would have taken values between minus pi and pi. And the implication of this operator, G here is the QC field strength, G tilde is this Hodge dual. So it generates a neutron electric dipole moment. No neutron EDM has been observed, which puts a limit on this theta bar parameter. It looks like it's tuned to at least 1 part in 10 to the 10. So a natural explanation is that there's one possible explanation is that there's an axion in the spectrum of nature. You can think that you promote this theta bar, which is a dimensionless parameter, it's an angle, to a scalar field A. But that scalar field has mass dimension 1, so there needs to be some scale in the denominator. That's the axion decay constant. You should think that this is some very high scale. And then this scalar field couples through this dimension 5 operator here. Now the implications of this are below the QCD confinement scale, you generate a potential for the axion. And as the axion minimizes this potential, if it's not at the minimum, there's a non-zero neutron electric dipole moment. But when it goes down to the minimum of its potential, the neutron electric dipole moment goes away, thus dynamically solving the strong CP problem. So let's just look at this potential a little bit more. If we expand out this potential, you see that the axion acquires a mass. So it started off massless. You can think maybe it was a Goldstone boson of the symmetry broken to the scale Fa. But now QCD has broken this symmetry, and so now it has a mass. The mass is inversely proportional to the decay constant. So taking a decay constant, for example, around 10 to the 12 GeV, you end up with a mass on the order of 10 micro eV. So most important for my talk today is that the axion also couples to electromagnetism through a very similar operator, AFF tilde, where F is the QED field strength. And there's some dimensionful coupling, GA gamma gamma, which you would expect to be inversely proportional to that same scale Fa. This arises model independently for the QCD axion from mixing with the neutral pion below the QCD confinement scale. But there could also be some UV contribution to this operator. So in general, I'm just going to put some C gamma here, where the C gamma is some property of the theory.
Is the model independent contribution of order 1, or is it very small?
In these units, the model independent contribution is order 1. I think it's like 0.5 or something. So also important for my talk is that the axion also couples to matter. It couples derivatively to matter to a, yeah. So the axion also couples to matter, derivatively to matter, to say electrons and to quarks, to all the fermions. And it's going to, these are all dimension 5 operators, so there's going to be that same mass scale in the denominator with some model-dependent coefficients, which depend on how you UV complete this model. This is not the theory I'm going to be talking about for reasons that will become clear. The theory I'm going to be talking about are axion-like particles, which couple to all of the rest of the whole standard model, everything I just said, except for QCD. So these particles will couple to electromagnetism, they'll couple to electrons, they might couple derivatively to quarks, but they're not going to couple to QCD. They might have some UV mass, and this UV mass, MA, I'm going to assume that it's small. But importantly, there is no mass generated from QCD since they don't couple to QCD. So I just want to point out that these CAQs and CAEs, the derivative couplings to electrons and quarks, even if you don't have them in the UV, they're still generated in the IR. They're generated at one loop. So you expect these matter couplings to be there. And one motivation, for me at least, to think about these models is that they, as people here have worked on, is that these axion-like particles seem to emerge from string compactifications, which just says that these are not the craziest things to go out and try to look for in data. I want to mention one paper which I found to be kind of interesting from Jim Halverson and company, which was looking at some specific compactifications, and they actually found within that framework the strongest coupled ALP could actually be relatively strongly coupled in the region of couplings that I'm going to be probing today. So just motivates looking for this kind of physics.
What is that as an effective decay constant?
So in an effective decay constant, you roughly want to multiply by 1,000. Yeah. So in their construction, most of they had a spectrum of about 100 or 200 axions. Most of them were more weakly coupled, but they found that there was a distribution of some that became more strongly coupled.
So that range is like 10 to the 7 to 10 to the 10, 10 to the 9 GeV effective decay constant?
10 to the 7, 10 to the 9, 10 to the 10 is roughly around what they were talking about. Okay, so now let's get a little bit more observational. So what are the current constraints on this parameter space? So what I'm showing you here is the constraints on the axion coupling to photons, GA gamma gamma, units of inverse GeV, as a function of the axion mass, units of EV. The QCD axion the coupling is inversely proportional to the decay constant. The mass is also inversely proportional to the decay constant, so the coupling is proportional to the mass. So for the QCD axion, you live in this yellow band. And it's a band because there's some model dependence in that coupling to photons. But if you talk about these axion-like particles, you can live anywhere in this parameter space. And so I spend a lot of my time, most of my time, thinking about the axions, QCD axion in the context of dark matter, but that's not what I'm talking about today. Today I'm talking about axion-like particles which might exist in the spectrum of nature, but don't have to have anything to do with dark matter. So if we talk about these axion-like particles, some of the strongest constraints come from the Cas experiment, which has excluded everything above this blue curve. And so I want to explain in a little bit more detail what the Cas experiment is.
Where's the red giant bound?
The red giant bound is essentially degenerate with the, well, here you can see horizontal branch stars, which are essentially degenerate with cast. Yeah. So cast, along with me, we both use this operator to try to detect the axion in exactly the same way. So here's the idea. Let's imagine you have some external magnetic field, which is static, and you want to send in a dynamical axion. Then in the presence of a static magnetic field, this axion can convert into an electromagnetic wave, which is polarized along the direction of the magnetic field. So if we can calculate the conversion probability for this process, you have a g here, there needs to be a g squared. There's a b here, there needs to be a b squared. And then just by dimensional analysis, there needs to be something with units of length squared to make that probability dimensionless. And so what is the length going to be? It's going to be determined by whatever scales are in the problem with units of length, which might be your external geometry. Say Cas, it'll be the length of the experiment. And there's another mass scale, which is the mass, or the inverse mass. So that might enter in also. And the difference between different experiments essentially just boils down at this level to what is the length scale. So what is the length scale for Cas? So what's Cas doing? The axions are produced within the sun through a process very similar to the one I'll be talking about for neutron stars. The sun is a KV plasma, produces the axions, they're relativistic. They go out of the sun, they enter Earth, they enter the Cas experiment, which is pointed at a strong magnetic field pointed at the sun, but of course they close the window, they put a wall up so that you can't actually see the sun. You can only see the sun if you're an axion and you can get through the wall. So then the question is, what is L? So this is an interesting question, and the reason is that the axion and the photon have the same energy, but they have different momentum because the axion has a mass and the photon doesn't have a mass. So the momentum mismatch scales like ma squared over omega, where omega is the energy of the axion. And so if the momentum mismatch is much smaller than the inverse length scale of Cas, you don't even notice that the axion has a mass. And then the length scale to take, there's only one scale, and the problem is the length scale of Cas. And you're happy because that's the biggest length scale you have in the problem. But when the momentum mismatch becomes big, so the mass becomes big, then you notice there's a momentum mismatch. Now the relevant scale that you're supposed to take is this inverse momentum mismatch. And now you're sad because this becomes small as the axion mass becomes large. So now if you go back to this plot, now we can understand this plot. At low masses, it's completely flat. And at high masses, the conversion probability drops off, and the sensitivity drops off. So you might ask, what are these wiggles? Well, Cas, these are smart people. They know about this. So what they do is they give the photon a mass. They put in a plasma. They adjust the pressure. They adjust the pressure. They adjust the pressure to scan over different masses. But they can only do that up to some point, which is why it's jagged and jagged, and then it just becomes, for whatever reason, experimentally too hard to do. So in my talk today, I'm going to be focusing on this region of parameter space at very low masses and couplings 1, 2, 3 orders of magnitude below where Cas is currently looking. And for me, the cutoff on the mass is going to come from a very similar process where when I'm at low mass, I don't even notice the axion has a mass. And when I get to high mass, I'm going to see my conversion probabilities start to become suppressed. And just to reiterate, for me, the axion is not required to be dark matter, but I do require these couplings to quarks or electrons or to matter, because that's how I'm going to produce the axion for most of this talk, not at the very end. But these, again, we expect them to be there. They might be there in the UV. If not, they're generated in the IR. OK, so now I'm going to overview how we actually calculate this signal, and then I'll tell you about the data analysis. So again, just to reiterate what I said, we need couplings to matter to produce the axion, and then we need couplings to electromagnetism in order to convert it into a photon. So let's start with this, calculating the flux of axions out of the neutron star. So the process that I'm talking about is very similar between neutron stars and white dwarfs. But it's simpler to talk about in the context of white dwarfs, so I'm going to introduce this in the context of the white dwarf. The difference is that white dwarfs have degenerate electrons, and neutron stars have degenerate neutrons or degenerate protons. But it's harder to talk about neutron stars because there's additional complications that come in. So I'm going to start by explaining this process in the context of white dwarfs. So in a white dwarf, we're going to have a similar process. We have an electron scatter off a neutron and a nucleon, and then we brim off this axion. So we're going to use this derivative coupling to electrons. So it is convenient to define a dimensionless coupling, GAEE, which is this, this model-dependent component CE, and then I multiply by the mass of the electron. This is just convention, but this is important convention because I'm going to use this notation throughout the rest of my talk. So GAEE is dimensionless. So in terms of this dimensionless coupling, the luminosity scales like the core temperature to the 4th power. If you go through the calculation, for a GAEE on the order of 10 to the minus 13, you get a luminosity which is not so bad on the order of 10 to the minus 4 solar luminosities. And the axions, as I mentioned before, will appear roughly thermal at the core temperature. So I just want to give some intuition for where this Tc to the 4th is coming from, where Tc is the core temperature. So we can break down the factors as the following. The thermally average cross-section, we get essentially one factor of Tc if you just go through the Feynman diagram of computing this rate. The energy, we're calculating a luminosity, so we need to take the cross-section and multiply by the energy. That's another factor of Tc. So now where's the other Tc squared? The other Tc squared is coming from the fact that the electrons are degenerate. So we're scattering within a degenerate medium, and so these electrons have to move into an open state. And they're only going to move into an open state if they're within Tc of the Fermi momentum. So then you end up with a phase-space suppression, which is going to go like Tc squared, Tc over the Fermi momentum squared. The Fermi momentum is on the order of an MeV for a white dwarf.
Why isn't the cross-section just 1 over f squared?
Are you asking about where does this where does the Tc come? I believe the Tc actually comes from a screening factor. If I remember this right. Yeah. Well, okay. Yes, the supernova. You're going from a different process. So the supernova, you typically look at the. I'll mention this towards the end. Is that you're actually producing through Axion-photon. But yeah. I think this might be coming from a screening factor, but I'm not exactly sure at the moment. So this is well studied. We're not the first people to look at axions being produced from white dwarfs. And the reason is that if you produce too many axions from a white dwarf, you cause the white dwarf to cool too fast. And so this is an example of how one of these constraints looks like. So what I'm showing you on the x-axis is the luminosity of white dwarfs and astrophysics units, where increasing luminosity moves to the left to smaller numbers. So these are more luminous white dwarfs. And this is the number. So you have the least number of most luminous white dwarfs. As you increase the axion coupling, you move from this solid line down, because now your most luminous white dwarfs are cooling faster, and you increase the number of low luminosity white dwarfs because they have to go somewhere. The total number of white dwarfs is conserved. So from fitting the axion model to this data, you can get strong limits on this coupling to electrons. Interestingly, I don't want to stress this too much, but there's actually a hint that this cooling curve looks a little bit better if you have an axion with a preferred coupling on the order of 10 to the minus 13. This hint has been around for a while. There's a similar hint with red giants, which gives you a coupling on the order of 10 to the minus 11, inverse GeV for the coupling to photons. Part of my personal motivation for starting this work in the first place was to try to rule out or confirm these hints.
That hint came from different data from the telescope?
Yeah. So the white dwarf. So I'm not even going to mention white dwarfs in terms of my data, but this data was just literally counting the number of white dwarfs at a given luminosity. All of the data that I'll be talking about is X-ray telescopes pointing at white dwarfs, looking for something, a signal where there should be no background. So the neutron star production is very similar. It's just a little bit messier. So we again have our derivative couplings to nucleons, which we can write out in terms of our couplings to up and down quarks. We again define a dimensionless coupling where we multiply by the mass of the neutron. And then the luminosity looks very similar, but there's now an extra factor of Tc squared. And so why is there an extra factor of Tc squared? So it's because now it's doubly degenerate. So before we had electrons scattering off of ions, only the electrons were degenerate, the ions were not degenerate. Now we have nucleons scattering off of nucleons, and both nucleons are degenerate. So that gives us an extra Tc squared suppression, which brings the luminosity up to scale. Is this very fast function of core temperature to the 6th power. And again, we expect the core temperature to be on the order of 10 keV. However, it becomes more complicated because the neutrons are also expected to form a superfluid inside of the neutron star. And superfluidity suppresses scattering. That's what superfluidity does. So when you're at a temperature much below the superfluid transition temperature, you have to tack on an exponential suppression to this rate. The typical superfluid transition temperatures are on the order of a few times 10 to the 8 Kelvin, but they're a strong function of density. So as you go within density, within radius, within the neutron star, the density changes, the superfluid transition temperature changes. So to do this calculation, you have to do this numerically, which is what we did, to actually simulate the full neutron star with its equation of state, put in a superfluid model, and then put in all the superfluid suppression factors and do this integral. But it even becomes more complicated because when the temperature is around the superfluid transition temperature, when you're actually forming the Cooper pairs, you can release the Cooper pair binding energy. And this process is known as Cooper pair forming processes, Cooper pair breaking and forming processes, which are an additional source of axions for core temperatures around the superfluid transition temperature, which you typically do reach because the superfluid transition temperature is a function of density, which is a function of radius. So
You mean breaking apart the Cooper pairs releases axions?
breaking apart or forming. Forming can also, because you're going into this potential well, you can emit that energy in terms of an axion. This is actually not very relevant for me right now because those axions tend to be higher energies because they pick up this binding energy, which tends to be bigger than 10 keV. So when I talk about follow-up observations, this will be very important. But for now, since I'm using telescopes which only really function below 10 keV, this isn't going to be that important. So there are constraints on this. Again, we're not the first people to go through this calculation. One of the best constraints comes from the neutron star Cas A, which is one of the youngest neutron stars that we know about. Cas A, you can actually see it cooling in time. So what's shown here is data from the Chandra telescope, where you can see the core temperature as a function of age. And these are ages over years, where we can actually measure the core temperature from one year to the next and see it decreasing. And it seems to be decreasing consistent with the standard models of neutron star cooling, which come from the same processes I'm talking about, but neutrinos instead of axions, which is how neutron stars typically cool, is from neutrino emission. So it seems to be cooling consistent with neutrino emission, which can set a constraint that's on the order of this number here. However, there's one caveat to this whole thing, which I don't want to go into too much, but it's also been pointed out that the energy calibration of Chandra is changing as a function of energy, which could completely explain this. So it is, I think it's currently an active subject of debate whether this cooling is real or whether it's instrumental.
Can you explain the x-axis?
Yes, the x-axis is time. Since 100 years. Here's 100 years where we didn't have any data because that was
The only data is in green.
the only data is in green. Yeah, good, sorry. The only data is in green. So we have data over about 10 years.
Oh, good.
And then I'm plotting the models.
This is very surprising.
Yeah, good. Yeah.
100-year
Yeah,
data.
the Chandra version 0. Yeah, good. Yeah, sorry. Okay, let me explain what the lines are. The black is the standard model with neutrino cooling only. Blue is let's crank up that coupling to axions. The caveat that I want to mention is that that entire decline that you see in green could possibly just be Chandra deteriorating over time.
I must say, this is really a case where the rest of the curve draws the eye. You know?
Yeah.
You're fitting this like
It's not my plot. I'm just, I would have changed the color scheme, but yeah. Oh, good. Yeah, that's the that is the this is the surface temperature, which is what you actually observe. The infinity means redshifted to infinity. Okay, so now let me mention something about the conversion process to photons, which is the other ingredient here. So now we know how to produce these axions, or at least I sketched what you would need to know to produce these axions. So the conversion is a little bit more complicated than what I told you for Cas. And it's a little bit more complicated because you're actually within, the magnetic fields around these neutron stars are around 10 to the 14 Gauss. And so you have to consider second-order effects. So for example, the Euler-Heisenberg term becomes important. So we've integrated out the electron. We have this f to the fourth terms, which appear here, where f is the QED field strength. And now you want to consider this f to the fourth term in the presence of a static external magnetic field. So you can think two of those f's become b squared. And then you end up with something which looks like a mass for the photon with only one specific polarization. So when you write out the mixing equations, or the mixing differential equation, you have a differential equation which mixes the vector potential parallel to the external magnetic field in the axion field. Delta A here is a term which involves just the axion mass. That's just the diagonal component for the axion mass. You have the off-diagonal terms, delta B, which are in here, which go like G gamma gamma. Those are the terms which cause the axion and the photon to actually mix together. But then you have this Euler-Heisenberg term, which has a B squared. And the relevant scale here is the critical field strength, which is just proportional to the electron mass. It ends up being around 10 to the 13 Gauss. So if your magnetic field is on the order of 10 to the 13 Gauss, then this Euler-Heisenberg term becomes important. And there's factors of the energy here because they're also derivatives acting on those field strength, and those bring down factors of the energy. So as you go to higher energies, the Euler-Heisenberg term becomes more and more important. For my purposes, this term is extremely annoying because what it is a big diagonal term in your mixing matrix, and it just suppresses the conversion probability. Additionally, the magnetic field is not a constant as a function of distance. For a neutron star, is typically assumed to be falling off as a dipole. So we have to put in that dipole form and then numerically solve this equation. You can also solve it in some limits analytically. So if you're at very low masses, then you don't notice that the axion has mass, and the conversion probability becomes a constant. And that constant is around 10 to the minus 4 for a G gamma gamma on the order of 10 to the minus 11 inverse GeV, which is actually not that small of a conversion probability, which is the reason that we can see this thing in the first place. You would have naively expected the conversion probability to scale like b squared. It scales like b to the 2/5, and that 2/5 is coming from that Euler-Heisenberg term suppressing the conversion probability. So you don't actually win that much.
What's the dimensionless size of, what is alpha over 4 pi m electron squared times b? I mean, that's the dimensionless. How important is the Euler-Heisenberg?
Yeah, so here is the critical field strength, which is me squared over E. And it's on the order of 10 to the 13 Gauss. And so I'm going to be talking about magnetic fields. Well, and then it's worse than that, because there's an omega here, which is the energy, which is going to be order of 10 keV. And this enters in the denominator here.
How do you call that the critical field? Shouldn't it be when b squared times alpha over m electron squared is of order 1? Isn't there an extra e and some 4 pi's in there?
OK, it depends where you put the 4 pi's. So there's a big tilde here. So there are 4 pi's which enter in the denominator in here. So it's actually it's a little bit smaller than it looks.
Is
yeah.
b actually big enough so the Euler-Heisenberg is an order 1
Yes.
to the photon propagator?
Yes. So yeah.
But,
and
then how do you trust anything then? Why keep
good.
these
OK, why just keep these terms? Yeah. So OK, so we have to be careful about what we're saying here. So B is big enough that this term is important for calculating this conversion probability, for the conversion probability. But it's still small. But it's still small. Yeah, it's still small. Yeah. OK, so we solve for this conversion probability. This is relevant when the mass is small, which, when you work this out, the only two-dimensional parameters are the radius of the neutron star and the frequency. So that's the condition which says if the mass is small or not. What does that actually translate to? That translates into a few times 10 to the minus 5 eV. After a few times 10 to the minus 5 eV, as you increase the mass, the conversion probability becomes suppressed like 1 over ma to the 4th. OK, so now let's talk about data. So I'm looking at the Magnificent 7. Why are they magnificent? These are 7 neutron stars close by, the closest known neutron stars, distances between 100 and 500 parsecs away from us. Remember, the closest star is about a parsec away. They were discovered with the ROSAT Full Sky X-ray survey, again, because they're only seen thermally emitting at low energies. And so you needed a full sky X-ray survey at those low energies to see them. Their surface magnetic fields have been measured with spin down. They're on the order of a few times 10 to the 13, close to 10 to the 14 Gauss. It's very strong. Their surface temperatures have been measured, and they're all around the order of 100 eV. And very importantly for this talk, no non-thermal emission has ever been detected. That means no gamma ray emission, no hard X-ray emission, and also no radio emission. So as far as before this work is concerned, these things are perfect black bodies. And they're also old. They have ages on the order of a mega year, which means they're isolated. They're far separated from their supernova remnants, so they're really isolated neutron stars. So I use data, and I'll be describing data from both the Chandra and the XMM Newton telescopes. And this data, I'll analyze it from either roughly 2 to 8 keV. For neutron stars with a particularly high surface temperature, I'll cut out the 2 to 4 band just to be careful. So this is in the regime where we don't expect any emission from the surface. So it is really nice that we have these different instruments for the following reason. Both of them are good at different things. So XMM Newton, there are actually 2 cameras on board XMM Newton, Pian and Moss. The 90% containment radius is about 50 arc seconds. This is a number which doesn't mean anything, probably, but just remember it for a second. 50 arc seconds, because I'm going to compare it to the number from Chandra. This turns out to be a pretty big containment radius. So what does that mean? That means the dominant source of background is particle background, extragalactic backgrounds, which just happen to produce photons within this 90% containment radius. So a big problem here are actually nearby point sources, which happen to be in our image. So you can imagine there's a point source, an extragalactic source, which is directly behind one of these neutron stars. That'd be very unfortunate. We might see a hard X-ray excess. It's not coming from our neutron star. It's coming from something behind it. Alternatively, an extragalactic source could be in our background region, which just means that our background is more complicated than we would have naively assumed. So that's why it's very important that we have data from Chandra. Chandra has a PSF, a point spread function, that's about 50 times better. So it's about 1 arc second. And typically, things go like this number squared. So Chandra is a much better instrument for making sure that you're not being bothered by nearby point sources. So they might ask, why do we even use XMM Newton data to begin with? The reason is Chandra has its own problems. One problem that Chandra has is it has pileup. So this is when 2 X-rays arrive on the CCD before the CCD is actually read out. Then the CCD might read that out as an X-ray with twice the energy. Or nonlinear things could happen. It could read out as an X-ray with 10 times the energy because it doesn't know what to do. Or it could throw out that X-ray completely because it doesn't look like a real event. So this is a problem for Chandra just because when the detector was built, it had a slow readout time. It's less of a problem for XMM Newton because it's a much faster readout time. So the fact that we have these different instruments which are good at different things is useful when we're looking at something and trying to decide if it's real or not. So this is the exposure time that we have available to us for the 7 magnificent 7, which I'm just showing you here by their first few numbers. So the first thing and this is exposure time in kiloseconds for these different instruments, which is what I'm plotting here. The first thing that should jump out to you is by far the most exposure time is from J1856. This neutron star has by far the most exposure time, and for a good reason. It is the closest one of the magnificent 7, so it is the best studied. It has a surface temperature that's around 70 eV, and its thermal luminosity, it has one of the lower surface temperatures, which means its thermal luminosity is relatively low. So pileup is not actually a concern for Chandra. So this was the first neutron star we looked at because it has the most exposure time by a decent amount for all 3 cameras. It's the closest, and pileup is not a concern. And this is the data that I showed you before for this neutron star, J1856. So what do we actually do to extract these spectra? So here is an illustration of how the data analysis goes for Chandra. We take the data and we bend it into 3 energy bands, 2 to 4, 4 to 6, 6 to 8 keV. We could go 8 to 10 keV. It doesn't change the story. The instrument's kind of degrading above 8 keV. We define a signal region and a background region, and we use the background region to estimate the number of counts which should be in our signal region. We do this with a profile likelihood in order to constrain the signal flux which could appear within the signal region. And then we also go back and verify that our background is actually describing the data in our background region at the level of Poisson noise, and it is. And so when we do this, what I'm showing you here is the test statistic for a fluctuation at a given pixel. The square root of this test statistic asymptotically scales like the number of sigma for your excess. And from Chandra data only, we see about a 3 sigma excess at the location of this of our neutron star. For Chandra, you have to be worried about pileup. This is what I told you before. So we did a full Chandra detector simulation where we simulated, now this is a spectrum, DFDE is a function of energy, we simulated the low energy spectrum, which is shown here in blue or in red. It's the same for both. We passed it through a full detector simulation. So in blue, we only simulated the low energy thermal emission, and the recovered data points for these 3 energy bins are shown here in blue. So when we don't simulate the high energy tail, we don't see the high energy tail, which says the detector is working as expected. In red, we add in the high energy tail. When we simulate it, we see it. And the gray points are our data points from actual data. So as far as the detector simulation is being a good simulation of the detector, we're quite confident that pileup is not a concern for Chandra for this particular neutron star. Here's the data, or one image of the data from XMM Newton. This is from the PN camera. So as I mentioned to you, you have to be worried about nearby point sources. So in this case, we make our background region quite small. So our background annulus is the region between our signal extraction region in solid red and the dash region out here. We estimate our background from that. We don't make it bigger because we're worried about nearby point sources. We have potentially identified 2 point sources. They're at very low significance, about 1 sigma significance. This one is likely just excess X-ray emission from this neutron star, which happens to have fluctuated up over there. We can't tell, but just to be careful, we do analyses where we model those point sources or we mask them, and it doesn't qualitatively change any of the results. The key point is that there's a big red square in the middle of this image where the neutron star is. From PN data only, this tells you there's about 4 sigma evidence for something going on at that pixel. And from MOS data, which is this other camera, doesn't have as much exposure time, there's about 1 sigma evidence that something is going on in that pixel. We've performed many systematic tests of this, which I can go through if people are interested, and it seems to be pretty robust. Yeah. Yeah, so color code is, again, test statistic. So this stops at 20. So you want to take the square root of that. Again, the test statistic is defined as a likelihood ratio for this profile likelihood. And then you want to take, really you want to Monte Carlo that, which is what we do to understand how it should behave under the null hypothesis. But assuming that things are going to obey Wilks' theorem, you can take the square root of this and call it number of sigma. And you're pretty close. Good. So for Chandra, we're signal limited. So most pixels don't actually see anything. For XMM Newton, I don't remember the exact number of counts, but I believe it's on the order of 10 counts, which is within the signal region. So in addition to J1856, we see this in a few other neutron stars. We see it, for example, in RxJ0420. This neutron star is really nice because there's absolutely no chance of pileup from Chandra. This is the lowest luminosity from surface emission of all of the Magnificent Seven. The pileup simulation just doesn't even register that pileup could possibly be a thing. And here is the Chandra data. And you can see that there's this bright pixel in the middle. From Chandra data, we see about 2 sigma evidence for something going on, which, again, you can roughly take the square root of that number. And then from PN and MOS, about 1 sigma each. Then if you ask about the other 7 of the Magnificent Seven, there are 1 sigma excesses in about 2 of the other Magnificent Seven, whereas 3 seem to be consistent with the null hypothesis. OK, so now what are the questions that you want to ask after you've analyzed this data? You should probably answer these questions in reverse. Is there another explanation? And then does the Axion model fit the data? But for the purpose of presentation, I'm going to answer these in the more exciting way first, which is to ask, does the Axion model fit the data? And then, is there another explanation? And if so, how can we test it? So to see if the Axion can explain these data, we have to know the properties of the neutron star in order to predict what the Axion model would actually expect for the flux. So we need to know, in particular, the magnetic field, the core temperature of the neutron star, and the distance of the neutron star. The magnetic fields are relatively well estimated from spin down, where you see the period decreasing over time. The distances, you'll notice some of these have tiny error bars, like RxJ1856. Other of them have massive error bars. The difference is that some of them have been measured with Gaia parallax, and others haven't. And the ones that haven't, you're then relying on some luminosity model, and the error bars are really big. We need to know the redshifted core temperature. This is the core temperature redshifted at infinity, which might sound hard because we don't observe the core other than potentially with Axion. So how do we do this? We estimate this from the surface temperature, and then using a model which relates the surface temperature to the core temperature. This model has a lot of uncertainty. It depends on the equation of state of the neutron star, which is unknown. It also depends on the accretion history of the neutron star, which is completely unknown even in principle. So this is actually our most dominant source of uncertainty because the rate scales like this to the 6th power. But we do have another way of, also magnetic fields could heat up the surface without affecting the core. So there's really, these uncertainties which are shown here in log space are probably an underestimate of the actual uncertainties which are actually going on. Luckily, we do have a different way of estimating the ages of some of these, where you can measure their velocities of the neutron stars. You can then trace them back to their supernova remnant. You can measure the age kinematically from that. Then you take your neutron star cooling model, where you're cooling from neutrino emission, and you run that code, and you see what age should the neutron star have, what temperature should the neutron star have now from neutrino cooling, and then you compare it to these temperatures, and they roughly agree. They agree within uncertainties. So we can do that for 3 of these neutron stars, which gives us some confidence that these error bars aren't crazy. And as I said, this core temperature is important both because it's affecting the luminosity, but also because it's affecting the spectral shape of the signal. And the spectral shape is roughly thermal. However, the conversion probability, if you remember that formula, did have an energy dependence. So you modify it slightly away from thermal to a bit of a flatter spectrum. OK, so now let me get to one of the questions which was asked at the beginning, where it was asked, is it flat? So here is that spectrum again from RxJ1856, shown here. DFDE is a function of energy, and black are the data points that I showed you before. This is now the joint data over PN, Moss, and Chandra, and in gray is the model. So at least at the surface, it seems to be, not at the surface of the neutron star, but on the surface of looking at this, it seems to be, the model seems to be doing an OK job. You can fit the Axion model to the data, and when you do this, you find the green and yellow bands. If you fit for that spectral form that I showed you before for the core temperature of the 2 neutron stars where we have enough statistics to actually do this, RxJ1856 and RxJ0420. And then you find the green and yellow for the preferred core temperature just to that spectral shape fit to the Axion model. You can then compare to those error bars that I showed you before from what we expect from our measurements of the surface temperature, what we expect the core temperature to actually be. And that's what's shown at 1 and 2 sigma in black and gray. So the spectral shape statistically is consistent with our expectation from the Axion model, although that isn't the strongest statement at the moment, just because we only have 3 bends and the error bars are very big. But it's consistent with what we would expect. Importantly, the spectra is hard, so it's inconsistent with being the tail of high-energy surface emission. The surface emission is falling exponentially at this point, and these spectra are rising. So I told you that we see this roughly in 4 or 5 of them and not in the others. You can ask, is that consistent with the Axion model? And the answer to that is maybe. So here is the intensity that we measure for all of the 7 magnificent 7 in green and yellow. Again, green and yellow is the expectation, or is the data. That's what we actually measure on the data. The black and gray are the theory predictions for these intensities evaluated our best fit Axion coupling. So we fit the Axion model to the data. We get a best fit coupling to matter. We then can ask, what is the prediction at 1 and 2 sigma from the model? That's what's shown in black and gray. So this is addressing whether or not the Axion model can consistently fit all of these 7 neutron stars. And so if you look, you can see the first thing that you might notice, maybe it's hard to read, this goes from 10 to the minus 22 in intensity, ergs per centimeter squared per second, 10 to the minus 12. This covers 10 orders of magnitude. so the uncertainties are huge on the theory side. And the reason is that the rate goes like temperature to the 6th power, and there's an exponential suppression from superfluidity. And we just don't know that core temperature very well. And because there's an exponential suppression, a small mistake in that core temperature can have a huge effect on the predicted intensity. This is only including the uncertainties that we do know. I, for example, haven't marginalized or haven't profiled over different equations of state, which would induce an additional uncertainty. So I think the summary is that from essentially this test is, yes, the data is consistent with the model, but it's just not that strong of a test at the moment. To make this stronger, you need to understand the neutron star equation of state better. You need to have a better determination of the core temperature in order to actually shrink those error bars down to the point where this would become a precision test. At the moment, it's just a kind of a general consistency check. Yeah?
Why aren't the uncertainties larger for the magnificent 7 that you observed?
Yeah, so these were the ones with the smallest core temperature. And so the smallest surface temperature, which translates to the smallest core temperature, which means you're most sensitive to that exponential suppression. They're also the ones that are closest away. So this is, the ones that are closest to us. So which goes hand in hand. So it's expected that there are many more of these neutron stars out to 500 parsecs. But these were the ones that are lowest temperature, are hardest to see, and they're the ones which are closest to us. So yeah, maybe it's just a coincidence. Maybe there's a deeper reason for why that's the case. But if there is a deeper reason, I don't know what it is. So if you combine all of this together, this is what this looks like on what this axis looks like interpreted on the plane of axion mass versus coupling to photons times coupling to nucleons. Again, this has units of inverse GeV because the coupling to nucleons is dimensionless in this way of defining things. So our best fit 1 and 2 sigma region fits down here below the best constraint to date, which comes from combining cast plus neutron star cooling limits, which may or may not actually hold. So at the very least, the most conservative thing I can say is we set the strongest limit on the axion within this region of parameter space. That's the limit shown in black. But then if you do interpret the model in the context of axions, you find this preferred region. We can't go to higher masses because then the conversion probability becomes suppressed because we notice the difference in dispersion relations. If you just ask statistics, a statistics question, you find about 5 sigma statistical significance for the axion model. That does not tell you there's 5 sigma statistical significance for axions. It just tells you the data is inconsistent with our definition of the null hypothesis at 5 sigma, which is a very different statement. So I believe that instrumental systematics are not important, but other astrophysical sources of emission are probably the most important thing when you're asking, is there something else which could create this signal? There are other constraints which are not shown here, which are relevant at very low masses, which I might touch on a little bit more if I have time at the very end.
Supernova constraint stronger than the neutron star cooling constraint?
Good. So the neutron star cooling constraints that I'm talking about are essentially degenerate with the supernova constraints on G8 and N that you've heard people talk about before.
Right.
They both have their sources of uncertainty. I would say the supernova constraints, they're essentially the same number. It's the same number to within 2 significant digits that you happen to get from this neutron star cooling and from those supernova constraints. Here, what I'm talking about is actually a different constraint, which is a constraint on G gamma gamma, which comes from axions which are produced in the collapse of the supernova, Primakov, which then convert into which can then convert into X-ray into gamma rays in the magnetic field.
Oh, I see.
It's a different constraint. It's a different constraint. It's not cooling. It's not cooling. There happened to be a gamma ray telescope operating at the time of supernova 197A.
I just don't remember how things are phrased in terms of the G. I was just asking, isn't the limit on exactly this combination that you're talking about stronger from cooling 87A?
No.
No.
No. No. Yeah. If you combine supernova 1987A in this mix, you get essentially the same thing, which is shown up here. Yeah. OK, so is there another explanation? So here are the models that we've thought of. And none of them seem to do a good job. But I'll tell you what we've thought of. One, could it be a more complicated atmosphere model? So maybe it's not the atmosphere model isn't a perfect black body. For example, maybe you have a hot spot on the neutron star surface. The problem is we've kind of gone over all of the possible models that there are in the literature. None of them seem to get close to describing the mission that we see, simply because the surface temperature is at 100 eV. The thing we see looks thermal at a temperature of above 10 keV. And it's really hard to modify a thermal distribution at 100 eV and get something which is a rising spectrum above 2 keV. So at least we haven't gotten any more complicated atmosphere models which could modify the spectrum away from a black body to actually do a semi-decent job of explaining what we see. Maybe it's non-thermal emission. Maybe these are actually pulsars. It is known that pulsars do produce non-thermal X-rays coming from, you have the pulsar jets, you accelerate electrons, positrons, which then cascade these electron-positron pairs and can produce non-thermal X-rays. The problem is, and I have a plot of this, but I'm just going to skip over it for the sake of time, but I can come back to it if people want to know more. The luminosity that you produce from the non-thermal emission is directly tied to the spin-down rate of the pulsar. Because as you emit non-thermally, you cause the pulsar to slow down. And we measure the spin-down luminosity. These neutron stars are known to be spinning down very slowly. And the luminosities, if you interpret the luminosities we measured in the context of non-thermal emission, it would actually overproduce the entire spin-down luminosity that we observe from the neutron stars. So the energetics don't seem to work. So you would need the non-thermal emission to not be causing the neutron star to spin down, which again then pushes you into a range of models which don't exist. The other thing is when you have non-thermal emission, you produce radio flux. And there's dedicated radio observations of all of these Magnificent Seven, and no radio emission has been seen, which also seems to rule out that explanation. Another explanation could be accretion of the interstellar medium, which maybe you're accreting the interstellar medium, forming an accretion disk. That accretion disk gets heated up, and you emit from there. Again, the luminosities and the energetics don't seem to work out. The luminosity that you predict from this is too low, and the energies are too low by about 3 orders of magnitude. So that is the temperature that you would produce doesn't seem to get up high enough. So, so I'm not going to say any more details about this, although I can kind of go into this more if people are interested. But at least none of the models that we have thought of seem to explain what we see.
Isn't it suspicious that it looks like the falling spectrum that then flattens out? Whereas you might have, I mean, you would expect it would look
Yeah, good, yes. Yeah.
It just looks like whatever the
Yeah.
whatever the falling
Yeah,
background is.
Yeah, so part of this, we haven't analyzed the data around 1 keV enough, which is where you need to analyze to actually see if you can see a dip, because it gets a little bit messy there. Because one, in order to model your expectation, you need to know. You need to have a model for that surface emission at very high accuracy, because you're now way down on that exponential tail. So now you become very sensitive to these atmosphere models that I was talking about before.
Your Axion model, you just change the parameters a little bit, like the core temperature.
Yeah.
I think the sort of typical signal you would expect would have been boom, and then.
Oh, but it's the power law, right? So we're seeing the low energy. If it's the Axion model, you're seeing the low energy tail of that power law. So I mean, what we observe is consistent with just the power law that comes up into an exponential, at least at the level that we're actually able to measure things and interpret things. It's consistent with just the power law. It would be different if it was a rising exponential instead of just this power law. But yeah, unfortunately, maybe one can tease more out of this data. I would certainly like someone else to look at this data and try to look at it differently. But yeah, we haven't been able to tease anything like that out. So, okay, what now to confirm or disfavor axions? I realize I'm running a little bit over time, so I'm just going to be quick going through here, but I can go through this more if people are interested. So the natural thing is to look above 8 keV, because as I said, the spectrum should peak around 30 keV, and there might be this other process which is producing axions from breaking Cooper pairs. And here I'm showing you predictions for the spectra as a function of energy. Blue here is where XMM Newton and Chandra have sensitivity. Red here is the energy range of new star, which is a telescope in the sky. And these different curves are different expectations from this particle breaking process depending on what the superfluid gap model that you take, which is a model for the critical temperature for the neutron superfluid as a function of density. So there are different models in the literature, and if you take different models, you get a very different result, ranging from nothing. Some of these models are degenerate with this bottom line, to some of these models predicting 2 orders of magnitude increase in the flux for given energies. And these aren't actually that bumpy in nature. It's just very hard to simulate all of these, so they're a little bit jagged just from numerics. So you might ask, why has NuSTAR never looked at these neutron stars? And the reason is that they didn't expect to see anything. These were expected to be thermal at 100 eV, not produce anything above a few hundred eV. And NuSTAR starts taking data at 3 keV and doesn't really start working until 5, 6, 7 keV. So we just put in a NuSTAR proposal for a follow-up observation of RxJ1856. So if anyone is on the NuSTAR committee, I think it's a solid science case. Hopefully we'll get that time and have data to tell you about in the near future. We also already put in a proposal to this exact same thing for white dwarfs. That proposal was awarded to us, so we do have time on Chandra coming up in March of this year, where we're going to look at a white dwarf. For white dwarfs, the exact same physics holds. The difference is that the white dwarf surface temperatures are at an EV, which is even lower, which is even better for us. The problem is an EV doesn't get up into the X-ray band, so no one has looked at any of these good targets before. There's no archival data available to us, because why would you have looked with an X-ray telescope if you don't expect to see anything, which for us makes them the perfect targets. So these are different units, because this is the coupling to photons times the coupling to electrons, but this is our projected sensitivity, which we should have in about 2 months. One last thing to mention, which we just realized like a month ago, is that you don't even have to convert in the magnetic field surrounding these stars. We were focusing on neutron stars because they have really strong magnetic fields. But remember, you're trying to compare b squared and L squared. So there's an alternative, which is to have a smaller b but a bigger L. And so what we realized is that you can get comparable conversion probabilities if you just convert on the intergalactic magnetic field, which is much smaller, but the length scale is much bigger. We can't probe as high of axion masses, because now we notice that axion mass more easily. But for ultralight masses, this is an alternative way of converting these axions to photons. The advantage is now we can ask not which star produces axions the best times converts them best, but just which star produces axions the best. If you ask that question, you're led to very young, hot, massive stars, like blue supergiants, or these Wolf-Rayet stars, because they're very hot. Their temperatures are huge, and they're also not that dense, which means they're not degenerate. You don't have the degeneracy suppressions. And you can also produce the axions through the GA gamma-gamma coupling alone. So let me just say 1 or 2 words on that. So I'm just going to skip over what these stars actually are. So the plasma frequency in these supergiant stars is on the order of 0.5 keV, which is much less than the temperature. The plasma frequency in a neutron star is on the order of 100 MeV, and a white dwarf is on the order of a fraction of an MeV, which tells you that you don't have propagating photons. And since you don't have propagating photons, you can't produce axions through the Primakov process because there are no photons. But in one of these supergiants, the plasma frequency is on the order of 0.5 keV, which is much smaller than the temperature. So there is a thermal population of photons, which can scatter off of the electromagnetic field sourced by electrons and ions, getting you axions from the GA gamma coupling alone. So let me just kind of flash to one result. We realized this. We then started scanning through all of the archival data sets available in X-rays. And we found that there was a cluster called Westerland 1 of very young stars with archival data, because it happened to be there's something else in the field of view that the people were looking at. But on the very edge of the image, there was our cluster Westerland 1 with all of these young stars. So we analyzed that data, and we looked for this process. And I will kind of show you what we find. So this is the data that we see. This is from NuSTAR now, because we're at very high energies. And we're able to set the strongest limit to date on the axion coupling to photons on the order of a few times 10⁻12 inverse GeV. we do find very mild evidence for something at the order of 1 sigma. I would not take that seriously. Because the evidence, so you're trying to compare these data points, which are the spectra, now going from 40 to 70 keV, to the Axion model, which is predicted to be here. We're at higher energies because the core temperatures are higher. We're focusing on these young, hot stars. And we happen to have archival data with NuStar. The reason is I kind of flashed over it. There was this magnetar right here, which is what they were trying to take the image of. And our cluster was right there. We just got lucky. They were not trying to take an image of our cluster. They were trying to take an image of this magnetar. And we got lucky, and there happened to be archival data.
What's the
Yeah.
how far away from the source
So
they convert?
this thing is about 2.5 kiloparsecs away. You don't have to worry about the Euler-Heisenberg term here because the magnetic field is a microgauss. So you're just literally multiplying g squared, b squared, l squared, a microgauss, and you get a conversion probability on the order of 10 to the minus 4 for g a gamma gamma of 10 to the minus 12, which numerically happens to be almost the same conversion probability I was talking about for the neutron stars. So we realized this very recently when we just started throwing these numbers around, that it happens to be almost the same numerical value as actually converting in a neutron star. And then the luminosity is big, on the order of 10 to the minus 2 solar luminosities for Ga gamma gamma on the order of 10 to the minus 12 inverse GeV.
Does this data tend to rule out the interpretation for the neutron star?
Good, yeah, so that's what I wanted to get to. Well, it's hard to say. So here is our exclusion. So our exclusion curve is in Ga gamma gamma alone. That's our exclusion curve. And again, we have a best fit value at around 1 sigma of 2.5 times 10 to the minus 12 inverse GeV, which is right around here. This is a function of the axion mass. Again, this is Ga gamma gamma alone because we're using Ga gamma gamma in this case to produce the axion and to convert it. So the first thing I wanted to say is this is the strongest constraint to date on this coupling. It comes close to the supernova 1987A constraint, but this constraint is much more model dependent than the one that we have here. So I think our constraint is much more trustworthy. Again, this is very preliminary. This could change a lot. And this is with archival data that just happen to exist. If you did a dedicated observation for this, you could push it down a lot farther. So OK, now if you're going to ask, is this consistent with what we saw before, I don't know, because you need to specify a coupling to photons and a coupling to nucleons to explain what I said before. Now we have a coupling to photons. So if you combine all of this, say you wanted to explain this best fit value, and you wanted to explain what we saw with the neutron stars. Suppose that was your goal. Then you are led to a value for these two-dimensionless couplings that I mentioned before, which would be Cn over C gamma on the order of 0.05-ish. So then you have to ask, what's your theory prior on that dimensionless coupling combination? And I don't know. So at the very least, it constrains the parameter space, which could be viable for that explanation. But without a strong theory prior, it doesn't rule it out. If this were to keep on going down and nothing were to be seen, then what would you learn? You would learn, OK, at some point, this is going to become a really big number. Because as you go down here, you're going to need a bigger number in order to explain that other excess without the neutron star excess without being seen here. On the other hand, this is cutting off at masses on the order of 10 to the minus 10 eV. The other thing went up to 10 to the minus 5 eV. So you would learn something about the possible mass, parameter space and mass, but then you would probably start to become more skeptical in general that if you had to be at relatively high masses. So I guess the takeaway is it constrains the parameter space. Yeah.
Why don't triangle diagrams kind of tie in decently?
Yeah, so there is a loop contribution to this operator. And that contribution is actually, well, it's also model dependent because it depends on how you couple to W's and Z's, because that's how you have to define your UV theory. But it's a little bit, naively, it'd be a little bit smaller. I think it would be around 0.001 if you just compute that from loops. So one question which I am very interested in, but
The electromagnetic self-energy of the neutron, right? Roughly.
yeah. One question that I am Yeah, I don't know. You need a theory prior. It looks like you would probably need some UV contribution to this operator, and or maybe unless you couple to favorably to the SU2 cross U1. But yeah, so I'm over time. Last thing I want to say though is that IAXO is a future Axion helioscope, which is going to be the follow-up to Cas. This is the big experiment. This is a tens of millions of dollars or $100 million experiment. So we actually beat them at low masses. I mean, the big advantage of AXO is that they're going to be able to go up to higher masses. But they'll be able to test some of this parameter space in the lab. But I think we can do better than them at low masses just with astrophysics.
By the way, the uncertainty you're referring to on the supernova limit is mostly just the temperature? The temperature dependent?
It depends on who you ask. If you ask Fear Bloom, he'll tell you it's not even clear if there was a supernova in the first, or if you formed a neutron star in the first place. And then, yeah, so if you agree that you did form a neutron star, then in the Gia gamma gamma limit, there's you have to model the magnetic fields over much bigger distances, and you have to model the supernova process. And both of these are more complicated than modeling the interior of a neutron star and the local magnetic fields.
Sorry, once again, your supernova limit here is not cooling.
It's not cooling. It's not cooling. It's conversion.
Isn't there a cooling limit on Gia gamma gamma and just from production?
It's not nearly as strong as the one from conversion. Yeah, yeah. So the conclusion is we found an excess of X-rays from these neutron stars, which could arise from axion-like particles. I really don't want to come off as trying to sell this. There is no astrophysical explanation that we've been able to think of, but in my opinion, that's the most likely scenario just because that's how our priors should be. I am pretty confident it's not instrumental, but if I had to put my money on something, it would be on some more complicated astrophysics going on within these neutron stars that we just don't know of at the moment. However, there's a lot of near-term work to test this. New star observations above 10 keV would be really useful. This is proposed. We have Chandra time on magnetic white dwarfs. Again, you're probing a different coupling, but it'll help narrow down the range of parameter space. We're working on analyzing more archival data kind of constantly, including what I just showed you before from these nearby star clusters. On the theory side, I would like to see other models. Maybe the Axion is not the only model out there which can explain this excess. Maybe dark photons could also explain this. We have not even attempted to model the inner core of the neutron star, things like possible exotic matter, production from a quark gluon plasma, or strange matter and muons. Maybe these are relevant. We just completely mask out the inner core of the neutron star in our simulations. We don't consider them because we don't know what's going on inside of them. It would be interesting to look, just in case that actually contributes to the luminosity. And from the string theory side, we're kind of shooting in the dark here. And if there's any more insight on the spectrum of couplings to matter, these sorts of things, at least in some explicit constructions or possible masses, I think that would help us know where to look in this multi-dimensional parameter space. So thanks.